Welcome back. This is Lecture 6b, Compilation via Optimization Frameworks, and I'm Jonathan Baker. In this video, we're going to give a high-level overview of a few optimization frameworks which have and can be used to solve compilation problems. One such technique from formal methods. We're going to discuss how these frameworks can be used to solve some of the important problems in transforming input quantum programs to ones which obey the constraints of target quantum hardware and can be executed directly. So we're going to take our problem and with some amount of cleverness, transform this problem into a constrained optimization problem. And then using, an out-of-the-box solver, get the solution to this problem, which will be a solution to our original problem. This video is going to focus specifically on the scheduling problem, but we could use these same methods to apply to many other problems like mapping and routing that we'll see next week. In many cases, the scheduling problem in this framework is easy to solve. For example, if all of the gates are specified and any number of gates anywhere on the hardware can be performed in parallel, then the problem is very easy to solve. For example, by assigning the starting time of all gates the maximum time of all previous gates, i.e. those with edges coming into it when examining the dependency graph. Let's see an example. So for example, if we want to assign the time to this node in our dependency graph, and we have many edges coming into this node, all with different times, say T1, T2, and T3, and we've already assigned times to all of the previous nodes. So maybe we call these H1, H2, and H3. Then the time of this node can be easily assigned as the maximum over H1 plus T1, H2 plus T2, and H3 plus T3. Because it has to occur after all three of these gates have finished. The easiness of solving this problem is limited by device level constraints. Let's think about one example. Suppose we have a device which has really high error when executing any 2 qubit gates in parallel. To limit this, we might add the constraint that says exactly one C0, or whatever our 2 qubit gate is, can be executing at the same time. This type of constraint, which has us make choices about which things can occur, can make the general scheduling problem much harder. Today I'm going to talk about a set of methods which are general beyond the scheduling problem, but what can be used to formulate these types of constraints and solve these general constraint problems. We'll apply them to the simple version of the scheduling problem and then talk about extensions from there. First, I want to talk about, at a high level, about linear programming, or LP problems. Linear programming is an optimization framework used to find the best value, either the minimum or maximum, of a linear function, where each of the variables is constrained by linear functions. We specify a linear objective, function f, on each of our variables. So f of x1, x2, through xn. Each of these xi are our variables. And the goal is to select which of these values, x1 through xn, is going to best minimize or maximize this cost function, which is given as some linear function of these variables. So c0 times x0, c1 times x1, etc., where each of these ci's is constant. So this is some linear function of our input variables. Each of these xi's is constrained by linear equalities or inequalities. And these constraints define a convex region known as the feasible region. This is the feasible region. Let's see an example of that. So this will be a very simple problem. So this region contains all of the points which satisfy the constraints. So points satisfy all of the constraints. The job of the linear programming algorithm, then, is to find a point in this region which minimizes or maximizes, whichever we're trying to do, the objective. So for example, we might want to find the objective, it may be to find this point here. Problems are generally phrased, however, in their canonical form. So for example, we're going to find, and using linear algebra terms, find a vector x which maximizes this function c transpose times x. So these c's are the same c's from above. There's some constants. Subject to, this st is subject to ax is less than b, or A is some matrix. And then we also specify non-negativity constraints that say each of the values of the x must be bigger than 0. And it should be noted that any problem can be phrased in this form. This type of modeling is very useful when both the objective and the constraints on continuous variables are linear, or if the exact optimal solutions aren't needed to be approximated by linear objectives and constraints. For example, problems in planning, routing, assignment, and of course scheduling, which we're talking about today, can be phrased in this language. Sometimes problems which don't immediately look like they can be phrased as an LP can be with a few transformations. Let's look at an example. Suppose our objective is to maximize the product of gate success probabilities. So for every gate in our system, we have this variable EG, which is the error of gate G. And we want to say that the approximate success rate of our program is to take the product of all of these things. This, of course, is not linear in these functions, but we can notice that if we take the log of these things, then this product becomes a sum. So then we're going to sum over the log of these things. And now this is linear in the logs of those error rates, which is now linear. So just with some simple transformations, we might be able to transform something that doesn't look in a good form into one that is. We just saw an example of a feasible region, which is this convex polytope. The functions bounding this region have the special property that any local minimum is also a global minimum. And that's what we can use to solve these problems. It is, however, possible that an LP problem doesn't have a solution. There are a few ways that this can happen. The first can be if our constraints over-constrain the problem. The feasible region is empty. There are actually no points which satisfy every one of the constraints. It's also possible for the region to be unbounded. So, for example, let's look at an example of an unbounded region. We might have the following region. Let's go on forever. Where it's all of the values appear. And if our goal is to maximize the objective, and so say the objective always increases as we increase along this axis. Objective increases. Then we could always keep picking larger and larger values to keep increasing the objective value, in which case there is no optimal solution. It's unbounded. When these two things do not happen, there is one or many optimal solutions, and the best solution always occurs on the boundary. The basic algorithm for solving this is called simplex. It's usually the first one people learn about. It solves the problem by constructing the feasible solution at one vertex. So let's just use the example above, but maybe we'll bound it to this larger region. It starts by picking a vertex, and then essentially it wants to look along the different directions that it can move and see if that changes the objective in a way that it improves it in some way. And essentially it'll just keep walking along the boundary of the shape of the region until it finds one that is optimal. Using this algorithm is very efficient, usually in about a cubic number of steps in the problem size. However, it's known that there are some worst case solutions which are exponential. So it's like often this type, but it can be exponential. It has been shown, however, that LP problems in general can be solved efficiently using other methods other than simplex, and it is a worst-case polynomial solution. So linear programs can be used to solve a wide number of problems efficiently, and it doesn't require us to write specific algorithms to solve them. Instead, if we can formulate our problem in the general framework, then we can use these known methods to solve the problem for us. Sometimes, but not always, this requires a little bit of cleverness to phrase the problem correctly. Of course, not all problems fit into this framework. A more general version of this is to consider variables which are allowed to not only be continuous, but also discrete integer values, or binary values if we're limited to 0 and 1. Say we're making a choice between whether to include something in a set or not. Both the objective and the constraints must still be linear, and we call these problems ILP, or MILP if the values are allowed to be continuous also. So if some of the values are continuous and some of them are integer, then it's mixed integer linear programs. The only major difference from the previous formulation is that now each of the xi's of our variables are integers. This is the set of integers, versus before these xi's were just some non-negative reals. Okay, let's look at an example problem. So say we have some region, and we've defined this area. This is from the LP. These are the constraints, the LP constraints. The ILP constraints will then, require that the values must be the integer parts inside of this region. So I'm just drawing the integer pieces. One way to approximately solve this problem would be to just solve the LP, to just look for what the correct LP solution was. Say this is the LP solution. And then to look at the points near it, the integer points near it, and see which one is the best one. It's not guaranteed to be the correct solution for the integer problem, but it might be close. This would be called an LP relaxation. And in fact, you need some extra cleverness into how to choose which point you round to afterwards. Notice that all of the integer solutions to the ILP version of the problem are contained within the region of the LP problem. In general, for even moderately sized problems, heuristics must be used to solve for ILP phrased problems. Let's turn now to see how these models can help us with parts of the compilation problem for quantum systems, specifically for scheduling. You should recall that near-term quantum systems are subject to a wide variety of errors and constraints on which and how many gates can be performed. These devices also have limited connectivity and limited coherence times. It is crucial to use aggressive optimization when targeting near-term devices with as many as 100 qubits. These qubits must be isolated from each other and the environment to prevent noise and errors from unwanted interactions. The coherence time of these qubits is on the order of about hundreds of microseconds to a few milliseconds. Here we want to talk about formulated compilation problems as constrained optimization and how we can use a satisfiability solver, which may make use of an ILP or LP methods underneath, to solve the problem. This approach can be used to synthesize compiled code, which is guaranteed to finish within a certain amount of time. We are focused on overall execution time, or the make span, which is the difference between the finish time of the last gate and the start time of the first gate. But other metrics in the objective could be used, as we'll see. The problem we phrase will be relatively easy. Isolating the scheduling problem alone in this way is easy to solve, as we mentioned before. But the difficulty of the problem can increase with only a few extra constraints. Optimal solutions for small systems can be found, and near-optimal solutions for devices a bit bigger than that can also be found. So let's go ahead and do it. The goal of the problem in the first case will just be to determine the start time for each of the gates in the circuit. We're assuming that some other compilation method has decided which gate implementations to use, on which physical qubits, etc. And therefore, we know how long each gate is going to take. The machine we're compiling to sets the maximum allowed time as t. This is the time that all gates need to be finished by in order to ensure they're all within their coherence threshold. The first step is to process the dependency graph, like we did in the last video. The dependency graph G, if you recall, specifies with its edges, I, J, in the dependency graph, that gate J must begin after I finishes. This is our first set of constraints. Okay, so let's write down some constraints. For every gate J, we want to introduce a variable that says that 1 is less than this T of J. So T of J indicates this is the start time of gate J. It must be less than this maximum allowed time T. We also want to make sure that every gate finishes on time. So we want to say that T of J plus the duration of J, so this D of J indicates how long it's going to take gate J to execute, must be also less than this maximum allowed time T. Then for each of the edges in our dependency graph, we want to specify another constraint that says the start time of gate J must begin after the start time of gate I plus the duration of I. This is for the edges I, J in our graph. This DI in our case is fixed. You can envision a problem where you might also need to decide DI based on some other constraints. This would, of course, would make the problem much harder to solve because you'd be making a choice of whether to do version A or version B based on some other parameters. For example, gate error or gate time, and balancing all of these things together makes the problem much harder. The objective is simple as well. We add in some dummy gate, G star, we're just going to call it G star, is dummy. And we constrain it to say that the start time of G star must be greater than the start time of Ti plus the duration of Ti, or of gate I, for all gates. This is the same as adding that constraint at the end of our dependency graph that said we had this infinity node specifying the end of the circuit. And we would just want to assign that the start time of that final node is after all of the other gates have finished. And then the objective is easy. Objective. We just want to minimize T of G star. We want the start time of this gate to be as short as possible so that the whole circuit is finished by a certain time. We've talked about other objectives in class before, for example, minimizing the active volume of each of the qubits. We want to minimize the amount of time from when it's first being used to when it's last being used in order to make sure that that qubit is within its own coherence time. In cases where the program is fully specified ahead of time, all we need to do is modify the objective. We can pre-process the dependency graph and determine the first and last gate on every qubit. If the qubits have varying coherence times, we may want to add the constraint that says all other gates finish in the proper window. So for example, the time when it's done would be the time of the last gate minus or plus its duration minus when it started needs to be less than the coherence time of it. So I've written this in plain language, but you could adapt this to a set of variables. So the things that are fixed are the duration of the last gate and the coherence time, and the two variables in this linear constraint would be the time of the last gate starts and the time the first gate starts, which is decided by the solver. The objective wants to minimize the total active volume, but you can think about other objectives you might want. So for example, you might want to weight different coherence windows to be more important than others. So for example, if we have one that's really short coherence, we might want to make sure that one's the prioritized highest. Hence we would weight it highest in the objective function. But the simple way is to just weight them all equally, and our objective would be to minimize the sum of the difference between of these things in the top. So T last gate plus its duration minus when it started, or the first gate. And so if we sum of this for all qubits, we can try to minimize the total active volume of the whole circuit. In practice, our simple version of the scheduling problem can be solved quickly. The first version is just an LP. But in more complicated versions, we need to do some approximation. We could do an LP relaxation as discussed before, relaxing any integer constraints and then round. Another strategy is to binary search on satisfiability. Instead of asking what is the optimal solution to this problem, we can ask a different question. Is there a way to solve a problem where the start time of that final gate is less than some fixed constant? So t, we should ask the question, g star is less than, let's say, t star for some fixed t star. And now we're asking the solver, can you find an assignment of those variables, of the start times, that will make sure that the program takes only this much time? And then what we can do is binary search over the t stars. Until we find one that's close enough within some approximation, like how close is the window between the last one that's satisfied and the current one that's satisfying. And if that window is really tight, then we know we're kind of really close to where the optimal solution should be. And often that's sufficient. So essentially we'll start with t star is equal to t, and then we set the lower bound in our binary search to be 0. Of course, we know that it's not possible for the circuit to finish in 0 time, but this gives us a very clear window that we need to search over. In practice, this is much more effective, and even if satisfiability problems themselves are also hard, when we're far from the optimal solution, it can be easy for the solvers to find satisfying solutions, often just trivial solutions, or counterexamples, that there's a path that clearly violates this duration, like it can't be done in that amount of time. And so it can easily kind of find or say yes or no to things that are far outside the window, or like not even close to the optimal. Okay, so in today's video, we've covered some important ideas in optimization at a high level. We introduced LP and ILP formulations of problems, where sometimes, if we don't know how to approach the problem otherwise, we can take advantage of already available frameworks. This kind of also allows us to take lots of different problems and stick them into one optimization framework. So if they're all related problems, and we don't want to solve them individually, we can try to solve them all together as a single algorithm. We then discussed how to put the scheduling problem into this context. We could then just feed what we just wrote, all of our constraints, into some solver, and then ask it to give us the answer, and then we would be done. Other problems like mapping and routing could be included in this model as well, so things that we'll talk about in the next few videos. Those, of course, will be harder because now we're making discrete choices about where qubits need to go or which paths to choose in the graph. You can also adapt these methods to take advantage of device-dependent errors that may change. And so you can adjust to make extra choices. And of course, the more choices we're having to make, the harder the problem might be, and the more approximations that we'll need to do.